Today's experiment is going to be the accelerated motion lab. It's pretty much a continuation of what we did last week. It's just continuing. I don't think there's really much need to go over theory. I will give just a little bit, but there are a few things I wanted to clarify. I was a very big failure at grading over the long weekend. I thought this will be cake. I'll have Sunday and Monday to grade. And so on Sunday, I was like, oh, I'll just do it all on Monday. And Monday I came in and I did some other things. So I didn't get very much grade done at all. But what I did grade, I actually looked at 2 labs, only 2. And the students, neither of them had the procedure section anywhere close to complete. They only spoke about like the first 5 minutes of the lab, and then that was it. And you need to have a complete procedure section. That is, you need to have a procedure section that somebody could reproduce, fundamentally, the lab by looking at it. So I put over here an example for this lab. Now, this is big writing, so it looks like it takes a page, but really this would take less than half a page. A low friction track, that's this, with a motion sensor will be level. I will then predict graphs of position, velocity, acceleration as a function of time when the car travels each direction on the track. My predictions will be compared to actual experimental results. That takes us through Roman numeral 2. Then Roman numeral 3, I will then give the track a small tilt, as you see now, and repeat the predictions and subsequent measurements. And then Roman numeral 4 is, finally, the motion of a ball thrown vertically will be predicted based on my understanding. Right? It talks about what you're going to do. You should be able to do the entire lab based on that description. Of course, I give you a lot more detail to make sure that people don't stray in different directions, and I have a bunch of questions for you. So that's what your procedure should look like. Now, that is not the same as your test. Your test is your test of your hypothesis. So going to the scientific methods section, you have your observation. Your observation needs to be something you see in life. Something. So I will steal from Brittany. Brittany's observation is, when I was a kid, I would go sledding, and I noticed that I would speed up as I went down the hill. Right? It's something that has to do with a change in velocity that she's seen in real life. So that's the kind of thing you should have for your observation. Then your hypothesis must explain why the observation happened. Based on the science of today. What's our science of today? It can be summarized right here. Your hypothesis needs to invoke that relationship, because scientific theory says that the change in velocity is going to be the acceleration multiplied by the time. So your hypothesis should say, using Brittany's example, that the sled sped up because on the slope there was a component of the acceleration of gravity that was down the slope, and because it had that component of the acceleration of gravity down the slope, the velocity should change according to acceleration multiplied by change in time. And so then this makes a prediction, so I'll just go straight to the test for my prediction. I'll test this by having the cart, and everybody should have, I will test this by having the cart go, and you can say up an incline, you can say going down the incline, or you can say going up and down the incline, depending on how you want to test. And my hypothesis predicts that because the acceleration of gravity should be partially down the slope, what's going to happen? As it's going up, the velocity should decrease because its acceleration is the opposite direction, or speed should decrease because it's opposite. As it's going down, the speed should increase. Your hypothesis predicts what would happen both going up and down. So while Brittany's situation was only going down, the hypothesis makes a prediction about going up as well as going down. It would be better to test the up because that's not testing a simulation of it, but testing a further extension of the hypothesis. Another thing that you could consider is, well, if my hypothesis is correct, then if I change the angle, like if I make it steeper, then if I plot my velocity versus time graph, I should have a steeper slope because the slope of the graph is the acceleration. If it's steeper, I have more acceleration down. There's lots of variations you can make on there, but your test is specific to testing your hypothesis. Your entire procedure is not your test, right? It's specific to testing the hypothesis. Is this clear? Right? Because what I don't want is people to be confused. I think I did it right. What? I did it completely wrong. Right? That doesn't help you. It doesn't make me happy. So we want to avoid that. Okay. Any questions about format or lab write-ups or anything like that before I actually start with my 5-minute introduction to the lab? Yes, Amanda. Ooh, that's a good question.
We're free on Sunday.
Sunday.
Yes. Friday and Saturday.
I like it.
Okay. I will get to this. I won't go all the way with Corso here, but no, he's working. You guys did notice that there's no homework due tonight, right? Because I did not talk about solving projectile problems in class on Friday. And so I can't give you homework solving these problems you've never done. Agreed? Yeah, okay. So I just wiped that one off the books. I renamed the original assignment, just incremented the number by one. So there is no homework 6. There's just homework 7 due Friday. Excuse me?
Are we talking the expert TA?
Yes. Or what?
The OpenStax?
Well, okay, the OpenStax, you have the reading quiz, and that continues on as scheduled. You have the supplemental homework there, which is just for your extra work, and so there's no reason to change that because that's just for your extra work. For people who want to practice more problems. So bottom line there's no change in the OpenStax schedule because the reading quiz stay the same. The supplemental homework is only there for supplement. It's not part of the grade. Okay, so that leaves, I want to make sure we're clear. I was going to send an email to everybody today, and I got forgot. On clarifying assignments. Another thing to keep in mind is that you probably lost access to Expert TA today, unless you've already paid for it. So today is the day that you need to go get that payment taken care of. But fortunately, you have until Friday for the homework to be due, so you actually have an extended period of time to get this taken care of. If you want to put it on your school bill, you can go to Terry Lair in the bookstore and she will work with you. She'll put it on her credit card. Actually, she was going to purchase some licenses, so she can just give you those and then charge your bill. If you don't want to put it on your school bill, then use your credit card and just do it the normal way. Okay, so when should the lab be due? I am happy to make it due the same time as the homework is on Friday. On Friday. Corso's like, this is not acceptable. You do know that Project Impact is only the morning and you have the afternoon free, right?
Let's just put it aside.
You have more time to get it done with Project Impact than you would without, is what I'm saying.
Let's just do it Sunday.
No, it'll be due the same time Friday as the homework. It's a compromise between Corso and where it was.
Saturday night will be the
Saturday night, any reasonable person is like, I'm not going to do any homework from sundown Friday night to sundown Saturday night. And from sundown Saturday night on, I got friends and things to do. I said that wrong, but let's not parse the words I just said. Okay. So, good question, Amanda. Any other questions? Like, do I know your name? Okay, so we already studied equation 3-1 last week, right? You did graphs of velocity versus time, position versus time, and you compared these things to learn how they fit together. So for today's lab, we're adding acceleration, and acceleration is, by analogy, exactly the same interpretation to velocity as velocity was to position. That is acceleration. The average acceleration is the change in velocity over change in time. We are doing only one-dimensional motion, just a straight line motion. So changing direction is not part of what we're doing. Hence, your observation, hypothesis prediction, or hypothesis test shouldn't deal with changing direction in the acceleration because we're not set up to do that. So we're just going to study this, look at the graphs. So we will now have 3 graphs, one with position versus time, one with velocity versus time, one with acceleration versus time. You've already studied the relationship between position and velocity graphs, but we have all 3 so you can now see how all 3 relate. Now, you're going to do the first part of the lab, just set up the track, you make it level. Look, I use this instead of a textbook. Everybody can do that. You're going to start with the track level. How do you know it's level? Well, I have in there, you put your card in the center of the track, give it a little tap in one direction, see how far it goes before it stops. Give it an equal tap in the other direction, see how far it goes before it stops. It seems to go a little bit farther one direction than the other. So I would adjust the feet here to raise or lower the height to make it level. Now, if you want something that's a little more sensitive, I can get out one of the little ball bearings. By the way, I'm 1 or 2 ball bearings short of what I had last Tuesday at this time. So if you like put the ball bearing somewhere like in a drawer. Yeah.
I think there were a couple in the engineering room.
Okay, well, yeah. If you know where a ball bearing is that I don't have, I appreciate getting it back because we use them every year over and over. But you can put a ball bearing on here. Ball bearing, you don't have to get a little tap, it'll roll. You will be putting the feet on the track. Let me give you some instruction on putting these feet on the track. First of all, you do not unscrew completely this nut. If you do, it leaves the nut inside the track and then the nuts get lost. So you don't unscrew it all the way, you just loosen it a little. This here slides into the channel. And so it's obviously easier to get it off than it is to get it on, especially when I have this here. And so it goes like that, and then you tighten it so it's not going to be loose on there. That's how you put the feet on. You have the feet on so you can adjust and level it. This here, the motion sensor, you're now going to want to take the motion sensor and switch it over to the cart, because we're using a cart. Why are we using a cart? You saw your graphs of velocity last week. They were not smooth. Using the cart, we will avoid humans who do a little wiggle as they walk, and we will have much better data using the cart. These jam on the end. Sometimes it's easy, sometimes it's hard. You want to make sure that this sensor is then in the vertical position. It has on this side indicators to see what the angle is, so that it'll see the car going all the way down the track and back. So that's putting everything on except for on the other side, we have here a stop. This stop has magnets on one side. You want the magnets pointing down the track. Those magnets are your bumpers, so the cart won't come crashing into there. The cart has magnets in it, and so it will be repelled. Now, depending on which cart you use, it might only have magnets on one side. If you only have magnets on one side, make sure the magnets are on the side. It's going to come to this. So the point of this is to keep the cart from crashing into the end when it gets there, because we want to avoid crashing. After you have it leveled, it asks you to predict what the graphs of position versus time, velocity versus time, and acceleration versus time when the cart is moving away from the sensor is going to be. So that's going back to what you learned last week. If you were walking away from the sensor, what would the position versus time graph look like? What would the velocity versus time graph look like? And then you're going to go ahead and say, what will the acceleration versus time graph look like? By the way, when you have carts in the pieces you're using are in the cabinets next to you. The carts, check the wheels. Make sure they spin. See, this cart makes me angry because this is the cart that we started yesterday when I did this with Noah. And all the wheels worked perfectly when we started. And then halfway through, something went wrong, and now 2 of them are sticky. If your wheels don't spin freely, so this one, it just stops, well, that's going to make your data not as good because instead of a low friction, it's going to be an intermediate friction track, you know. So try to check your wheels, and if your wheels are bad, choose the other cart in your cabinet. If your wheels are bad, you know, like take the cart to me and say, hey, this thing has bad wheels. So we can try to take the ones with bad wheels, set them aside. At some point I tell Alex, take these 2 screws off, slide that little metal thing out, see what the heck is wrong with these wheels. Yes, sir. So check those wheels. This has a lot of friction because it has 2 bad wheels. So it's going to stop pretty quickly. After, note the after part. After you've made your predictions and explained why you came up with your predictions, then you're going to take data with the cart going away slowly, and then with it coming toward it slowly, answer a few more questions, take pictures with it going rather rapidly away and rather rapidly toward, save that to include with your lab. Then we're going to tilt it. So I know the lab guide says use your textbook. We don't have a textbook. I really need to change that, don't I? But the power supply is a great substitute for the textbook. Just slide that power supply under here, and now it's tilted. And it says to push it up, take a few tries just to see what it's going to do. You want to push it so it goes at least a meter up the track. For the 2.2 meter long tracks, you want to go at least halfway up the track. And the further it goes, the more fun. So I give it a push. That would be good enough. Give it a bigger push. That would be too hard, right? Because while it didn't touch the bumper because of the magnets, it was definitely affected by the bumper. And that would show up in my data. So give it a few tries to figure out how hard to push it. You're going to then answer, again, a number of predictions. Make sure you answer the predictions before you do the actual measurement. There's no point in the predictions if you've already done the measurement. You're just identifying what happened. The predictions is to see that you understand it, and if you don't, so you see, ooh, I didn't understand that. What did I miss? Right? So there's actually a real solid reason for doing the predictions before you do the experiment. So then you'll push it up, let it come back down, take those graphs, scale them, print them. Make sure you do scale the graphs appropriately so that you fill the vertical space. Then the final part of the lab is not an actual experiment, it's just a prediction. You're going to take what you learned and say, when I throw the ball up, what's the velocity going to be like as it goes up? What's the acceleration going to be like as it goes up? And you just answer questions based on what you learned. So the final portion, part 4, is not doing an experiment. It's showing what you learned. Okay, any questions? No? Okay, let's go with groups of 2.